Hello community, so great to see you. Let's talk about super intelligence in AI. And yes, we have it published today by Princeton University. Yeah, Meta, I'm so sorry. So let's have a look. Now, we have our classical DeepSeek model, 671 billion free trainable parameter, Kimi K2, 1 trillion free trainable parameter, mixture of expert 32 active. But what is the other side? The other side is if you do not have 10,000 GPUs. Imagine you are just a single person. So what you use LM Studio, you have local elements, you have here maybe Olama, you have a C++ implementation, and your hardware size matters. Yeah, if you are lucky, you have 16 GB of VRAM on your GPU. So you see here, this is here widening to an extreme. And now there's a beautiful and clever idea by Princeton University for a super intelligence AI. Let's examine this. Now, very simple, LM Studio community, let's take a Mistral, a small model, a 3.224B. And if you have a Mac, it's a little bit better, né? So the option that you have is, you pay about 10,000 euros for a 96 GB here, a workstation, a Pro 6000. Or if you like Apple, great, Apple M3 Ultra with 96 GB here in Europe. It costs you about 6,900 euro. Cheaper, but not really great. So what we have is a prevailing paradigm. No? The AI landscape is here defined by the scaling hypothesis. Bigger, even more. Models like GPT-4 and Gemini are trained here top-down on massive text corpora. I always say they copy the internet. But you know what it creates? Polymaths. Models with a phenomenal breadth of knowledge capable of conversing on nearly any topic. But the AI intelligence that should emerge is an emergent property of scale, and of scale only. And this is now the question. It is great in generalization, but is also the critical weakness of this polymath, no? Because the knowledge is wide, but very shallow. So it lacks verifiable grounding. So if you are working here in domains like medicine, engineering, science, you have a problem of unreliability with the current AI systems. So we can now face, if you want, a choice. Do we want to go and scale the generalist model, the GPT-5 for all the people here on this planet, absolute generalist, absolute huge? Or do we say, let's stop this, this is nonsense. What about we build here specialized AI, much smaller specialized AI, but make them more intelligent? So how can we teach here an AI here an axiomatic compositional logic of a domain and not just put in here the complete internet, but be more intelligent if we build those models? And here we have from Princeton University, Department of Electrical and Computer Engineering, a beautiful new study, July 18, 2025, Button-up Domain-specific Superintelligence by Princeton. A reliable knowledge graph is what we need. Anyone said, how is this possible? Well, it's a very interesting paper. They introduced a null task synthesis framework that traverses a structured path on a specific knowledge graph to generate a reasoning task, but not in the normal way. Those reasoning tasks directly generate some abstract domain-specific primitives for the training. And they have now a new foundational claim. And they say, domain-specific superintelligence. So not everything for everybody, but really for medicine or for physics or for material science. Domain-specific superintelligence is not an emergent property of the scale of the model, but an inducible property derived from explicitly training a model, an LLM, on a curriculum of proofs, mathematical proofs, sourced from a domain axiomatic primitives. Anyone says, yeah, of course, this makes sense. No? Your last two videos were exactly about this, or PPL, or we talked about Lean, or we talked about DSPy3. But now those domain-specific axiomatic primitives come from or are encoded in a reliable knowledge graph. So we say, hey, let's make it easy. Let's make it simple and let's go with a knowledge graph. So they say now, hey, you know what? Knowledge is not found in terabyte of if we copy the internet, but knowledge is now constructed for a domain-specific and even task-specific use case. So let's build it. So the old way, top-down intelligence, showing here a model, the entire library of human knowledge and letting it learn some statistical patterns, even if we have no idea what the model is learning. And the new way is now, hey, let's construct an intelligence, and then really design an intelligence by teaching now an LLM the foundational axioms, the alphabet if you want, and the rule of the composition, and then train it to write its own paragraphs. You see, it's a complete upside down that we say now how we should train the next generation of LLMs. So you might go and say, hey, we have knowledge graph. What is special about this? Well, it is not the old knowledge graph that you might know, no? Because now in the core abstraction here of the new paper, you can say that a knowledge graph is now a formal system in mathematics. No? A knowledge graph is not just anymore a database of facts or any vector representation or a vector space or a tensor structure. It becomes now a formal system of learning. So a triple, head, the relation, and the tail is now an axiom. It's a foundational, non-provable truth. And a path on a knowledge graph is now a theorem with a proof. A path proves a higher-order relationship by chaining the axioms together. So this particular path here, for example, is not a proof of the theorem A to C. So you see what we are doing? We are not going here with a normal graph reg system. We are not going here with, say, hey, an LLM operates now and traverses your knowledge graph that we showed you from MIT. No, we have now a complete new idea. We build up the logic from the ground up. Here we have now, they give us an example and say, okay, here we have 200 nodes, the top 200 nodes of a medical database. And then they say, great, but what we are interested in is, of course, here, the distribution of the edge type in our knowledge graph. And here we have it. For the top 200, you see here the most prominent edge type that we find in the medical database is here, maybe cause something. And then belongs to the category of, may treat something, belongs to the drug family of, is a risk factor of, is a subtype of, interacts with, may contraindicate this. So you see this is the edge type. And now we have just to translate logic into a learnable lesson for a new AI system. And you might say, hey, easy. So how do you teach a neural network that is more or less naked? How can it learn now from those specific kind of examples that master now a formal logical system? Now the author said, hey, we have the idea of a curriculum foundry. And the task of the foundry is exactly to translate some abstract knowledge graph proof into a rich, verifiable training dataset. You see the word verifiable in the training dataset? So now this gets now interesting. So let's have a closer look at this. The curriculum foundry. This is the engine that drives the creation of our new super intelligent expert model as nominated here by Princeton University. The foundry is more or less a 4-stage process. Let's have a look at this. Path traversal, a question and answer generation. We still go with a trace generation, and then we just have to filter. You think, hey, this is all simple. This is all known processes. There's nothing special. Well, let's have a closer look. So here you have now from the official publication by Princeton here, the complete view. You have data, you do here a diversity sampling, a complexity sampling, I'll explain in a minute. Then you have your Q&A generation, you have a quality filtering, you have some LLM generating here a trace, a thinking trace generation. Plus you have 2 additional LLMs that are here the proofreader and say, hey, we make sure only if 2 LLM agree at the same time that this will pass here the filtering process. And then we have it, no? Then we have our training data. Then we can train our next generation of AI. Easy, no? Well, that's not so easy. Stage 1. Sourcing here the proofs from the universal medical knowledge graph. So, systematically sampling logic chain from the expert-curated unified medical language system. Great. We have a path of length n. We can define this here. It's a sequence of n connected axioms. Great. This gives us now a raw symbolic material for the curriculum, no? A set of theorems and their explicit proofs that we can start with. You see this here in the initial node selection and a path traversal. Great. The sample path is now mapped, the next step, to a natural language Q&A task. By prompting it, guess what? We need another LLM, a very intelligent LLM. So an abstract path, in the simplest case, we just take A, B, C, is not a useful training example. Yeah? It must be grounded now in natural language because we will use a large language model and not large logic models. So if we use still language, we have to go a little bit in a circle. Now we need a powerful LLM, and this is now our problem setter. The prompt is give me a path, create a clinical vignette, and a multiple choice question testing the relationship between H0 and Hn. So the reasoning required to solve now this question must exactly mirror now the logic of the provided path. The proof. Here you have it, for example. Yeah? We create here a medical examination question for yes, and this is the information given. And here, question and options. And this is now the generation here of an example of a generated Q&A pair, where the text highlighted in green is now entities revealed in the question, and the blue highlights indicate latent entities. Oh yeah, of course, because we use here the parametric knowledge of a huge LLM, let's say the Gemini, yeah? So we know a lot of context about this. And now we integrate everything because we use here an LLM to build up here this language sequence. Generating the gold standard thinking trace. No? The model needs to see what perfect reasoning looks like. So for each question and answer pair and state-of-the-art reasoning, Gemini 2.5 Pro, they used here the latest, yes, they is prompted now to generate a step-by-step thinking trace. We need here the logical thinking in a natural language. So prompt includes now the ground truth knowledge graph path as the context, anchoring thereby the reasoning in verifiable facts. The facts, everything relates back to the knowledge graph. And the result, pristine human-readable proof that becomes now the target for supervised fine-tuning. So here I show you here a concrete example that you get a sense of what this structured rationale looks like. Thinking trace here of a created training curriculum. So we have for this particular knowledge path, a question generated, options, and now we have here Gemini 2.5 Pro, the thinking trace. And look at this. This is now really some extreme detailed, if you want, training data that we can start now to train our large language model. But the logic behind all of this are the the traversed path on the knowledge graph that were then later translated just by an LLM into some reasoning traces in the human language. And now this is now the training data set for the fine-tuning of the next, if you want, language model. And they say, you know what, we need a verifier. And it's not possible that we just accept what comes out. So they have a dual key verifier. So this is the most critical quality control mechanism. Eh? They say the full dataset triplet of a question, the trace, and the answer is presented now to two independent LLMs. And now, after they went with Gemini 2.5 Pro, they go now with Gemini Flash and a QN system, or maybe you go with an open source system, a DeepSeek or a GPT-5. If you have this already when you watch this video, you get the idea. So you judge if the answer is given, and every claim in this trace I just showed you are logically and factually supported by the source knowledge graph path. If there is a derivation, if there's a hallucination that happened during the generation here of those traces, it will be detected, hopefully, by one of these two additional LLMs. So you see we have now 3 LLMs working in tandem. And the data point here, this triplet, is accepted into the final curriculum for the pre-training only and only if both graders, both LLMs agree on its correctness to 100%. And if not, you have a feedback loop, you get the idea. So you want to make sure no hallucination, no, oh, it just some leftover from such sort where the chain of thought was incomplete. No, only if both systems agree. What a nice idea. So this is exactly here in the flowchart where we are right now. Now, at the beginning of the flowchart, diversity and complexity sampling, rather easy. There's a lot of formula, but I just give you here 1-2 sentences. The probability of the sampling here, a particular node I, is inverse proportional to its select frequency. So what you want that the entire wide of a knowledge graph is now sampled. So you don't want that, let's say the knowledge graph, if we transfer the knowledge graph in a vector space, that it is just operating in one little corner of this space. You want that the whole space is completely now taken and probed and examined. So you don't want here that you have only an overfocus on some common medical conditions. You want everything in your data to be here sampled. Nothing is left out. Plus you want a complexity sampling. So this means you start easy, no? A 1 hop, 2 hop, 3 hop. Now it starts to get a little bit complex, 5 hop, 7 hop. You want to mirror the human learning. You start easy. You don't start with the most complex relationship. No. Start simple, and you want here that the complexity 1, 2, 3, 4, 5, 6, 7 hop are represented here accordingly. Here you see it. The curriculum entity distribution, and here you have all the medical specialization. And just look at this, no? More or less, yeah, everything is not really evenly distributed, but yeah, okay, that looks good, yeah? So at least you have thousands and thousands and thousands of samples here for each element here in this medical subsystem. And then just have a look here, this 3 here at the bottom, yeah? Here you have in whatever this is, hop 1 syncing trace token distribution, beautiful. A hop 2, a hop 3, great, looks perfect. So we have achieved what we set out to do. The curriculum structure is really representative for each medical sub-element or sub-knowledge if you want. And we have a beautiful distribution of 1 hop, 2 hop, 3 hop, and whatever. And now we are ready, tells us Princeton University. And now we can do it, no? Now we take here any model, let's go with an open source QWQ. You see, Princeton relies on open source models. And now we have the training data set, and now let's do a supervised fine tuning. So we have now a MAT3 LLM. Yeah, beautiful fine tuning happened. You see here all the parameters of the fine tuning process, great. And now we have it. And they decided to go with 3 models, MAT1, MAT2, and MAT3. The 1 hop axiom, so they're very close together. This is here MAT1. If you have a 2 hop proof integrated, MAT2. And if you go for a full deep curriculum with up to 3 hops, MAT3. 4, 5, 6, but would cost more. And then they decided, okay, this is great, but you know what? We need a new benchmark. We need an evaluation suite of new unseen Q&R tasks, because everything is known on the internet, no? We want to make sure that this is really unseen evaluation. This is a new independent evaluation. So from 15 distinct medical specialties, they extracted now long, complex path, 2 to 5 hops, and they reserve this especially for the evaluation. So they have really a test data set that is not available, is not contaminated here, anything in the training data. Great. Yeah, if you want to see here the ICD bench, this is here the top categories, and then you see here sample Q&A items. If you are into medical, into diseases of the nervous system or diseases of the eye or mental, behavioral, or neurodevelopment disorders, you will enjoy this literature. But let's come back to the AI topics, no? Let's come back to superintelligence. Why Princeton is talking about superintelligence? Well, it's a little bit here to get your attention, no? But what they want to really stress is here the emergence of domain-specific highly intelligent AI system. And they say this new LLM that they trained have a significant performance advantage over all the other baseline, all the models from Gemini, everything else. this training here is superior for creating here deep domain expertise. So you see, we didn't just copy the complete internet and build a model with 1 trillion free trainable parameter. We went with a simple QWQ model. No? So great, we found a new idea how to train smaller open source model on domain knowledge. Now, they did here a medical knowledge graph and they generated 24,000 tasks to abstract to diverse medical primitives. And now what is the result? What is the performance data? And you see it here in the arrows indicated here. So what we have for all the different medical subsectors. Oh my good. Here, there's an overall if you want. So we have here 4 LLMs. The first one here in green is O3 from OpenAI. Then we have here Gemini 2.5 Pro from Google. Then we have here QWQ, the base model, the 32B base model. I mean, imagine a 32B compared to an O3. I don't know the model size of O3, but I would guess 32 is really a smaller one. And then this new model that Princeton created here, the MAD3. On the overall performance plus close to 16%. This is a lot of today. 16% improvement here on domain-specific task is gorgeous. Think about it, we have a 32 base model that we just fine-tune. And it outperforms O3. Not bad. I guess O3 was trained on the complete medical library that is available for free on the internet. Of course, respecting all the intellectual property rights and whatever. But real nice performance from logical primitives. Unseen training. How robust is this under pressure? And they said, okay, as the task complexity increases, more and more reasoning steps. If we go more and more complex, now the generalist model collapses. And I have some independent tests on my channel. I can tell you, yes, there are, you can see exactly up to a certain complexity and then there's just a cliff. There's nothing left after this. Eh? And they say here, this new MAD3 performance degradation is far less severe. Its advantage over the baseline widens on the hardest problems. So, and they argue because this model internalized the understanding of the knowledge graph, the logical primitives that control this domain, that design this domain, that build up this domain knowledge. No? So they have the structural logic foundation, and then they have no problem to attach here or cope here with complex unseen logical chains because the base is there. What a nice idea. And of course, we have to see this. So look here on the left side, you have here the accuracy on the y-axis and the difficulty on the x-axis. Oh yeah, so we start for the very easy task. Every LLM has 100%, but then the harder it gets, my goodness, the performance accuracy goes down to 0%. Only those 3 very colorful LLMs you see here, they stay above everybody else. They are the best here. And those performers are our new MAD1, MAD2, and MAD3. And exactly MAD3 is the best. Absolutely fascinating if you think this is here benchmarked against an O3 by OpenAI and the actual Gemini 2.5 Pro by Google. And you have also a DeepSeek R1, now the distilled Q132B. So if you see, this is here, let's say the Q132B in distilled. So this is quite a performance jump. Of course, the more harder the multi-step reasoning becomes, it goes down the performance, but nothing compared here to the other models. No? It outperforms an O3 in medical. So beautiful. Okay. Yeah, they have another idea how to visualize here the reasoning gap. No? They say we have a powerful diagnostic now to separate the model's ability that recalls the fact versus the reasoning with the facts. No? And yeah, I just show you here. If you want, you have a look in detail here on the paper. They give you here, in the first one is the QWQ32 base model. And then we have MAD1, MAD2, and MAD3. And we have this here for hop 2, hop 3, hop 4, and hop 5 questions. Now, what is important is the color. Look here, the task reasoning accuracy is 60% is blue and 100% red hot is red. Now you see blue, dark orange, and the more hops we have, the harder it gets in the reasoning chain, the better the performance becomes. So really nice if you compare this here. Now, the dot size is the recall and the color saturation is the reasoning accuracy. Visually disentangle the two concepts and show how the base model has large pale dots, so recall without reasoning, while the MET3 has large saturated dots with reasoning, high accuracy. Really interesting. And then they said, but watch out, what we found, and I just showed you the data, the MET3 is the best. So the most complex one with the highest training data set has the best performance. So this means a deep curriculum with multi-hop in the learning data has the best solution in the reasoning capabilities. Of course, this is exactly what we expected, no? And they tell us, yeah, so just learning here the theoretical axioms of medicine is insufficient. You need explicit training data on progressively deeper and more complex proofs, because you will be in the test, you will have real multi-step reasonings, tasks that you have to master. No? So the deep structure of the curriculum is vital. Yeah, here I have you for MET 1, 8,000 tasks, single hop, MET 2, 16,000 tasks, a 2-hop path, and MET 3. Here you have all the 24,000 tasks over 8 epochs here, 3-hop paths included. This is the difference. You can have here the scaling, the inference time scaling, but just let's look here, the last two here in the bottom, the parallel scaling across the model with a refinement across the models. I just tell you the result. It turns out that if you have the deeper curriculum models, no, having acquired more structured and more diverse knowledge graph primitives, benefit more from exploring multiple reasoning paths in parallel. If you do here computer optimization in parallel, it is better if you have here the complete model with the complete 24,000 training data and the 3 hops. They have a better parallelization for multiple reasoning path realization. It was expected. So very simple example that you can see it. This is the path. This is the question. And now the response is simply this. So there's nothing magic. It is just the system learned here the basic logical structure. Now, if you do it here in a real example, not in a simplified that I just showed you, here is a screenshot here from the study. And here you have now a knowledge path from the disease of the respiratory system, the question, the option, and then you have here the MET3 response, and you see exactly how from a simple path here, you can generate here now a correct answer in the real example. What does this mean for science? It means that any domain that has a structured knowledge graph, that has an inherent logic like genomics or law or material science, anything with science in it, no, finance, mathematics, can now adopt this particular pipeline by Princeton University to build really specialist AI model. And you do not need to pay here the global corporation like OpenAI or Microsoft or whatever for the huge generalistic models. Because it turns out for a very narrow domain, the specialists are much better in their performance on reasoning performance than a generalist model, because it just learned everything that is to learn on this planet. So it moves here the creation of an expert AI from an art reliant here on scale to a more deterministic engineering discipline where you start with the logic principles. It is kind of a long-standing goal, no, for neurosymbolic AI to be successful by fusing here the logical rigor of symbolic system with the power of neural networks. And I think this publication here by Princeton is a beautiful example for this. But careful, there are limitations. Let's talk about the limitations. The source, the knowledge graph, is the dominant factor. No? If the knowledge graph is incorrect or missing traces or missing complexity or missing relation between the object on your graph, the resulting LLM cannot reason beyond this axiomatic base. So the knowledge graph, at least for the simplest logic base, has to be kind of complete. And there's a beautiful example, and I already showed you this, the path length now. If you take 10,000 and the distribution of the shortest path length in the knowledge graph, in this particular medical knowledge graph that Princeton looked at, you see the path length, so the number of edges, the multi of hops, for a 4-hop logical chain was here, if you want, the dominant one. And for 7-hop, we just had 31. So this is here the training data set. This is here the learning essence. So if you have now, let's say, a complexity of 8, how the hell should the AIs know about it? The training stopped at 7. There's no miracle that suddenly some intelligent emerges here from the background. This does not exist. So if you look at here, this is a beautiful example. The structure of a knowledge graph dictates the maximum complexity of reasoning that the new AI model can be trained on. Because the pipeline generates here the training example by traversing those paths on the knowledge graph. And if the longest, most complex proofs available on the knowledge graph are 7 steps, like here, only 31, then it is impossible for the AI to create a training example for a 10-step logical deduction for a reasoning path that includes here 10 steps. And there is nothing of emergence suddenly in the background here coming down from the sky, and now the AI has the ability to go for a 10-step logical deduction. This is not happening. This is a hard cutoff in its ability, what complexity this AI can handle. The positive part is you can see this very easily with a graph analysis. If you look at the knowledge graph, that you see how complex the knowledge graph includes complexity, and if this is enough for your task, for your domain, what you want to achieve with this AI system. What are the next step? What about expanding this to more generative tasks? Princeton says, yeah, we are thinking about it. Yeah, because the next question, and we will have a look at this in my very next video. Now that we have built expert AI systems that are perfect reason, are built on logic, or not on autoregressive next token prediction, how can we combine this with fact verification like GraphRag, Can we build now a self-correcting reasoning agent that uses now its internalized logic to form hypotheses and an external knowledge graph that is maybe updated much more frequently to verify now this in real time? Oh, this gets interesting. Absolutely. But okay, I think this is it. Let's have a summary. So what we achieved. We built a new class of AI, a domain-specific superintelligence specialist, as published here by Princeton University. So we are shifting now the focus of complete AI system from the statistical mimicry of saying, hey, I want to predict the next token based on my training set that is just here a copy of the internet, to the explicit construction of compositional logic. And it provides here a path towards AI systems that are not just more powerful, but also more reliable, more auditable, and deserving now our trust here in the field that matter most. Because we can say we build on logic and we do not build on statistical patterns alone. So a very nice idea. Of course, we have multiple LLMs in between, generating here the right training data set, and something can happen, some hallucination can happen, as always. But if you have the base right, this is a good first step. Here, if you want to have here everything here together, step 1, step 2, step 3, step 4, we went through everything. I hope you enjoyed it. If you like it, subscribe, and I see you in the next one.